Hello. So I'll improvise a little bit. The slides are double-checked, but I have not rehearsed. So I quit Google, and after a few months started a passion project building a neural networks framework in OCaml from scratch. And since a few months, my work is sponsored by Ahrefs, of which I'm proud and thankful. So what's OCaml? So it's a bit confusing, OCANNL with a double N. It stands for OCaml compiles algorithms for neural network learning. Or also it stands for OCaml Neural Nets Library. It's distributed as two packages. Hopefully someday the ArrayJIT package would be helpful for other approaches to numerical programming in OCaml. And OCANNL compiles at runtime to efficiently execute numerical programs. And there are many such frameworks in other languages. In Python, there is TinyGrad. It's a startup by George Hotz. He quit his startup, comAI, where they work on self-driving cars, driving assistant. And he concluded, when you try to do machine learning in Python, training deep nets in Python, you incur a huge dependency cone with millions of lines of code. He decided that that's too bad for his heart. He wants to see what's the minimal code base that you can do convenient and efficient deep learning in. And that's a bit of a motivation for my project, but it's very far away. In Rust, there is Luminal, which is also compiled neural networks framework. Luminal is mostly interested in inference on small machines, but they also support training. And in Rust, I counted 6 neural networks frameworks. And in OCaml, I'm aware of OWL, the OCaml Scientific Computing Library, but not of other approaches. And I think it's worthwhile to explore multiple approaches. And as will become clear, OCANNL is definitely not the approach. It's one of at least 2 approaches beside OWL. So maybe one of at least 3 distinctively valuable approaches to a deep learning framework. So what's added? What OCANNL brings to the table? It has quite powerful shape inference, meaning inferring the dimensions of matrices. It has more expressive shape representation than the run-of-the-mill approaches, and type inference is as powerful as I could think of. And since OCANNL is explicit about when you compile, it might be good for heterogeneous computing, but it's also a bloat overhead in your code. So I'm thinking of one day adding another convenience layer that will maybe become clear later. So it's definitely a proof of concept. It's not efficient yet. Maybe not too bad on CPU, but GPU just starting. It will grow and it will definitely evolve. So I hope to get a bit farther with the project by the time I present, but since I didn't, let's focus on one toy example. So we will train a feed-forward neural network with 2 hidden layers. So it will be a 3-layer MLP, and we will classify points on a plane. If you've ever seen TensorFlow Playground. That's a website over a decade old, I think, by Google, where you can see how training a network looks like. And here I provide some notation that we'll use in following slides. So we have a hidden dimension. We have our data set we'll see soon. We have batch size, we have our parameters, W1, W2, W3, and so forth. We have ReLU, rectified linear unique, as the activation function, and we have weight decay as regularization. So what's neural networks training? It's a gradient-based optimization problem. To learn, we first need to collect a data set. So these are the examples that we're trying to approximate. Then we need to represent the solution as a parameterized function. That will be our model. So a particular neural network is a model. Then we need to figure out how to score that solution on the data set. That's going to be the loss function. And then is the training loop. We need to figure out what's for a particular point from the data set, what's the direction that we can take the parameters to improve on that data point. And then we need to somehow make the parameters better, knowing about that direction. And this approach to optimization or training is called stochastic gradient descent. All right, but we don't just proceed point by point. We batch the points, and we combine the gradients of points in a batch. And that's where the stochasticity comes from not exploring the points in a fixed order all the time. Well, let's see it on the next slide. So we can select the batches randomly, or we can permute the data set before each run through the data set, because often we'll want to go through the data set multiple times. And that stochasticity actually improves the properties of training. But in my example, I actually stick to a particular partition of the data set for simplicity. So that's our data set. It's known as half moons, although it looks more like overlapping horseshoes. It's a synthetic data set. I can generate it at the start of training. By the way, this sign means I can rush through this slide. So what's the model look like? It's composed out of matrices or multidimensional arrays we call tensors. Those arrays, by being part of an expression, they are actually transformations, not just numbers. And in OCANNL, I segregate access of a tensor into output access, which are the regular access of vectors, for example, and input access, which would be the dimension of a matrix that's matched against the dimension of the vector to apply the transformation. In OCANNL, I also introduced batch access, which replicate a vector or a matrix. And that's how our toy example looks like in a single line of code. So going through it from the right, the X is the input to the network. The multiplication here is the matrix multiplication. More generally, it's a tensor multiplication. There can be multiple access. The string, it's a notational shortcut to inline declare a tensor. Here we provide the output dimension of the tensor B1. So that's the rectified linear unit nonlinearity. And then the whole function takes a tensor and outputs a tensor together with a computation attached to it. In OCANNL, each tensor will have a computation attached to it that computes the expression to obtain the value, the array of the tensor, and for differentiable tensors also to obtain a gradient with respect to some function of choice, meaning the loss function typically. So this is more of a declarative notation for tensor expressions. So next step is to find the loss function. We'll stick to the simplest, which is the hinge loss function. It's simplest because it's just using the rectified linear unit nonlinearity. The motivation comes from support vector machines, where we try to find the biggest margin separation between two classes. So once our classification gets good enough, bigger than 1, we're happy. Otherwise, we try to push it in the right direction to classify the point accordingly. So regularization, it's the component of the loss, abstractly speaking, which tries to keep a model simple, and meaning that will mean that it's less accidentally wrong. So if you introduce complexity that's not well motivated by the data set, that can overfit, adapt to spurious properties of the particular sampling of the domain we want to learn. So we'll just use weight decay. All right. So now, how do we derive the computations we're interested in? How do we derive the gradients that attach to tensors and tell us in which direction to modify parameters? So OCANNL uses backprop. I think this is the most straightforward approach, easiest to understand. It's a special case of reverse mode automatic differentiation, but out of the box doesn't allow to compute second order gradients. So it generalizes the chain rule. In the computation of the gradient, we'll need the values of the sub-expressions within the compute within the tensor expression. So the forward pass is how you would compute an expression typically. And then the backward pass is how to derive gradients. And the gradients will be with respect to a fixed target, like the Ross function, but they will be attached to the tensor with respect to we compute the gradient. So df over dx will be attached to x as x dot grad. All right, so details of the backward pass. We add up contributions for each place that x appears. And the order of computation is reversed with respect to how values are computed. So first we compute df over dy, if y is a function of x, and then you can use that to compute df over dx. But it's still the same order of composition. So we can have the tensor y on its own with the computation attached to it, and then use that to for the computation of f, of the gradient. And that's because that computation is specific to y. When we have tensor y, we have no idea about f yet. So when we have tensor y, we have its we can have gradients of subtensors within y. So specifically, once we have y, we will know dy over dx, and now we encounter f. So we can just prepend the things specific to f. So we prepend df over dy to the computation dy over dx, and that's how we get the computation df over dx. So here it's an example for multiplication. A quick interlude about how computations or code that's generated is represented in OCANNL. So we have a sequence of assignments. These are accumulating assignments. So that there will be some left-hand sign to which we accumulate computations from the right-hand side, and those computations can be unary depending on one tensor, or binary like addition multiplication. And the accumulation will often be addition, like when we want to add up gradients, or just proper assignments when we don't accumulate. And accumulation can optionally reset the tensor before the assignment starts. So then we accumulate from within a single assignment, or we can keep the left-hand side as it was before, which we will want to do for accumulating across multiple expressions, like in when we need to compute the gradients. So that's what another syntax extension, CD, is all about. And so now, how will we express tensor operations in OCANNL? We need to provide the forward and the backward code. But first, there's notational shorthands for, this is for the proper assignment, and this is a shorthand for accumulating assignment. So the op code is for the forward pass, the grad code is for the backprop pass, and in the backprop pass we don't reset. We accumulate all of the occurrences of the gradient. There are some extra shorthands. So G2 is, let me step back. We have an operation add where T is the result of T1 plus T2. Maybe let's see it here. So in the forward pass, T value will be T1 value plus T2 value. And in the backprop pass, we backpropagate the incoming gradient G into the tensors T1 and T2, and specifically T1 grad and T2 grad. So here's another operation, subtraction. So specifically, the gradient will also switch, invert. And here is the operation for multiplication. And so the forward pass will be just multiplication of values. And that looks quite mysterious, how that can be any sort of multiplication. And that's because we implicitly accumulate across axes that only appear on the right-hand side, but not on the left-hand side. So for pointwise multiplication, we will have proper assignments where there is no accumulation going on, and in the matrix or tensor multiplication, we will accumulate those gradients missing on the left-hand side, those axes missing on the left-hand side, but we'll reset the value first to not confuse it with other multiplication assignments. And for the backprop pass, to compute the gradients, we multiply the incoming gradient by the value of the other tensor. And that follows quite easily from the differentiation calculus. That's on page 21. And also, those projections argument, they specify what the axes are like for the left-hand side and right-hand side. That's how we can know which axis to accumulate over for matrix multiplication. All right, let's skip this one. Division. So it's quite concise, as you can see. It corresponds quite closely to the symbolic notation. So the gradient we propagate to tensor 2, it's the incoming gradient times this tensor expression, which corresponds to T1 times gradient T2 over T2 squared. So now we put the forward pass and the backward pass together as a single computation to get the gradients. We should not forget to clear the gradients from a previous training step before we start accumulating them again. This is a notation for block comments, and they are used to provide names for files that we can send to C, for example, to a C compiler, and they also help with debugging. So how to best update parameters once we know the gradients? So this vanilla way would be to just subtract the gradient from the parameters, since a loss is a bad thing. So we want to go in the opposite direction of the loss. But that can be slow when the loss space is smoother, when there's less variation in loss. So then to speed that up, we can accumulate gradients over consecutive steps, make the training step bigger in that way, and also make the training step less susceptible to the stochasticity in the batch by combining it with gradients from the previous steps. So that will be, so the momentum will be geometrically smoothed by the momentum coefficient values of gradients of the parameter of interest. So let's skip this slide. So that's the stochastic gradient descent update expressed in OCANNL. And here we have inline declarations of those helper tensors for accumulating gradients, like the SGD momentum we saw in the previous slide. There is some extra notation to make sure we derive the projections in a pointwise way. Make sure that this is a pointwise computation when we multiply by the learning rate. So this assignment is the same as the assignment where we have just a plain tensor expression. But this one is unary. There's just one tensor on the right-hand side of the assignment. And here is two tensors on the right-hand side in terms of the assignment syntax. That's just a peculiarity. All right. And so getting something out of the computations, we need to select a backend. So what we'll use for compiling, here it will be a C compiler. We'll create a device. So if a CPU has multiple cores, we can derive a device for each of the cores of the CPU. We initialize a context and the computation will be a routine that's attached to a device. And in the simplest example, we can just put together the backprop computation of gradients with the update of the parameters in a single routine. So that's what we get in the high-level notation of assignments. This is taking a slice of the data at a particular batch index. And that's how it gets compiled to a low-level representation, which gets optimized with inlining. All right, so let's run through the slides. And since we've been proceeding step by step, you can look in the slides on what comes next, and in part and specifically it does work. It trains a classifier on a plane. Thank you.
And thank you, Lukasz. This was interesting. Yeah, just round of applause for. I think that running neural networks in OCaml totally deserve it. Any questions to Lukasz? So I see you're sleeping, right? Yeah, then for me, one, did you test the actual performance comparison with, like, I don't know, at least Python examples?
Not yet. It's coming in a few months.
Oh, sure, yeah. I mean, but at least like an approximately, how slower it will be.
For the C backend, an order of magnitude slower. For the GPU backend, it's just proof of concept at the moment, so it will be 3 magnitudes slower or even worse.
I see. Okay. But still.
But it's not so hard to optimize the C backend. I can see a clear way to getting on par for the C backend.